Welcome back. We had the first test yesterday. Some people were obviously very happy with their results, some not so happy. To make sure that we understand where we are after the first exam, remember you do have one drop exam. So if this score was unacceptably low, it doesn't mean you're doomed, but it does mean that you would be best served to figure out, okay, why did I not do well on this when I thought I'd prepared? Because you all were prepared, right? I assume everybody, spent time preparing for the exam, and so those that were surprised by the scores were surprised. So if you have questions, both about the grading of the test or the answers, or how to do them and how to prepare better for the next test, please come see me. My office hours are posted out there. If you see me in my office, even if it's not office hours, if the door is open, that means I am willing to help you. So just come on in. Don't be like, oh no, he won't see me now. Because I want to make sure that we, the collective we, all experience success here and not failure. To that end, after we have 3 students, those 3 students I already said, Ryan, Lydia, and Nathan. Lydia's not here. After... Yes, it's not just you. Yeah. After they come up and do a homework problem, that's one of the ones that's due today, originally due a week ago. You remember the process of delaying twice. Then I'm going to look at a couple test questions, do a couple problem-solving force problems, and then we'll throw it back to you once more. So, gentlemen, since Lydia's not here, come on up. And your problem is the rocket sled one.
I love rocket sleds.
I've never been on one. It does. And this being the second time around, do explain to the class what you're doing as you go through it. Oh, good news. Here she is.
Lydia, come with us.
Oh no. I knew this was going to happen today.
In fact,
What's
take the
up?
lead.
Yeah.
Oh.
Yeah.
Good thing I did this one this morning.
Oh,
Yeah, good,
Yes.
good.
Wait, hold on.
Come on up,
I'm
Lydia.
exercising
Everybody give her a
because
hand.
I was like, what am I going to do for grade?
Thank you, Lydia. Let me see if I know. No. Nothing off the top of my head.
You guys that are steadier and left because Lydia said she did it this morning.
Yeah, exactly. So what we're going to be doing is reading through the question first. It's a good place to start.
No,
Yeah.
What question
Leslie
is this?
laughed, but that's something that I need to emphasize more because it's a problem that I make. I'll read part of it and then go through and solve the wrong question.
I did that on the test.
Oh.
Actually, I don't
Oh,
think I did
sorry.
this one.
Real quick.
So I'll just go ahead and read it.
Oh, actually, I did do this question. Okay, we're good.
The mass of the system of the rocket sled shown in the figure is 2,100 kilograms, and the force of friction opposing the motion is known to be 675 newtons. The thrust for the rocket sled is 2.5 times 10 to the 4 newtons. What is the acceleration in meters per second squared?
Okay. Should I just do it, or do you guys want to help me out?
No, yeah. Talk us through it.
Okay, so all right, so our acceleration is going to be the thrust minus the force, the net force,
So first we're coming up with
divided
our
by our mass.
equation that we're going to use.
Okay, good job.
And we're going to fill in the variables that we know.
Okay, our thrust.
Write the known ones down is step 2 of solving an equation, I think.
Oh, we're running out of room. Let's move it down here. Minus the
T is our thrust.
really great commentary here.
Net force is the force of
Okay, does
friction
anybody have a
opposing the
little-
motion.
Calculator. You gonna calculate that?
And there's our mass.
I'm going to calculate stuff.
Okay.
And so
Oh, yeah.
She's ready.
I'm just ready for the number.
Got it.
12.
Well, I guess significant figures, so 3.
So newtons is kilograms times meters per second squared. So when you divide by kilograms, you end up with meters per second squared. We got 12 meters per second squared.
All right. Any questions for these intrepid explorers?
Do we
Thank
get it?
you
All right, thank you.
for no questions.
Thank you for no questions.
I feel that.
Now, one correction I would make, I'm not taking off on your points here. You started with Newton's second law. This is a Newton's second law problem, which says the net force is equal to mass times acceleration. Now, you look at the picture, and you actually have to use some wisdom here. In what direction is it going to accelerate?
Right.
Okay, I'm just going with horizontal. To the right is correct, of course. So as we learned previously, we have independence of motion. The vertical and the horizontal I can do completely separately. And so I'm only going to take the sum of the forces in the horizontal direction is mass times acceleration in the horizontal direction. And I'm going to ignore the normal force, what's labeled as N here, and the force of gravity, what's labeled as W here, because those are not horizontal. They're vertical. But if I look at the picture, we draw the forces here so we can use Newton's second law. So if I look at these, I had T going forward, so my net force has T going forward, and lowercase f going backwards, so minus f. And then the final step on this to solve for A would be AX is equal to T minus F over M. And then everything they did from there on was correct. What you see, well, what do you see that's different between the equation I have in the box and the equation that was written down? Okay, A sub X instead of A. That is true, but it's not really significant to our outcome.
I just talked about the horizontal forces.
Right. Now, she only did horizontal forces as well, but there's a nomenclature thing. And this is actually an important thing. She wrote, instead of the force of friction, F, she put force net. The force net is the thrust minus the force of friction. And so that's an important distinction. And so when you're doing these problems, I strongly encourage you to always start with Newton's second law, and then just looking at your diagram, figure out what the sum of the forces is, and solve it that way. All right. I come here, I look at a lowest scoring problem on the test, and then I'm going to go back to the other document to work on it. So the lowest scoring problem, a rocket starts from rest on Earth and accelerates vertically at 22.3 meters per second squared for 89.3 seconds. The rocket's then cut out and it continues in free fall. And it asks us what the ultimate height is that it reaches. So just to make sure that we have this in our head straight, if I take this ball, I can treat this ball as the rocket, and my hand will be the rocket, and the rocket thrusts it up for a period of time. And then the rocket stops, so my hand's going to let go. But what happens to the ball after it leaves my hand? It's still going up. And we need to find the ultimate height that it reaches. So we have two stages here. Stage one is when the rocket is providing propulsion. Step two then is when it's in free fall. Here, step one is while it's in my hand. Step two is after it leaves my hand when it's in free fall. So I'm going to go back to the OneNote page where I can give myself more room and just remind ourselves we have stage one Oops, that's y0, not y1. Actually. So those are the variables I know and don't know for stage 1. I know the acceleration it has. I know the time that it's going to take. I know that it's starting at an elevation of 0 and a speed of 0, but I don't know the end of height or the end speed for stage 1. Then for stage 2, free fall, the only things I know right now are A2 is equal to minus 9.80 meters per second squared, because it tells us that we're going to assume that the acceleration of gravity remains constant throughout. And we know that V2 is equal to 0. It didn't tell us V2 is equal to 0. How do I know V2 is 0? When does stage 2 end?
When it becomes
At its highest point, and its highest point, the speed is 0. So that was an implied thing, not a number that was given. And I'm looking for y2. So ultimately, this is my goal, to get to the y2. Notice there's v1 that we will get from here, and y1 that we will likewise get from there. So I'm going to have to solve this problem in 2 steps. Define y is up. I'm going to draw a picture here of the acceleration as a function of time. And so it starts at 22.3, and then at time 0 it comes down to negative 9.8. I don't know why my parentheses didn't. That's what the acceleration looks like. Now, based on that, we've done in lab, we can draw what the velocity graph should look like. If you have constant acceleration, what does that mean for the velocity graph? Uh-oh. Lab, have to think back a week ago yesterday. If you have constant acceleration, what does the velocity graph do? Straight line. So we're going to have a straight line. Whoops, I put velocity where I meant time. I'm doing well. So I'm going to have a straight line, a steep slope, because that's a positive value. The slope is the acceleration. And then at 89.3 seconds, it shifts to a negative acceleration, which means a negative slope that's a flatter slope. And it's going to get to 0 out there. 0 velocity, that's when it's at its peak. So that's going to be the time when it is at its peak. And now if I were to graph position versus time would have gone something like this, where you have here it's upward acceleration, upward curvature. Out here it's downward acceleration, downward curvature. So I've got graphs to go with these, but I need to do the calculations. So sticking with the red here, stage 1, I have the acceleration, the time. I'm looking for the final speed and the final elevation for stage 1. How do I find, let's go with the final speed first. Given those variables, I can find the final speed. What equation is easiest to find the final speed if I have time and acceleration? Not that one, because that doesn't have V final in it. It's the V final is equal to V initial plus acceleration times time. So I just put in my initial speed was 0 plus my acceleration of 22.3 meters per second squared times 89.3 seconds. And that gives me a speed 1 of 19.91 meters per second. So I'm going to write that in right here. 1991 meters per second. I put a point in there that doesn't belong. So there I have my speed at the end of stage 1. What about the elevation at the end of stage 1? That's going to be the one Ryan said. And so you put in the numbers there, and that gives you, don't remember all of it, 88, what? We just wrote it down, Hannah. What is that number? So write that here. So now we found the conditions at the end of stage 1. Now we're ready to go on to stage 2 when it's in the free fall. So looking at the variables we have for the free fall, acceleration, the initial velocity, the final velocity, the initial height, I'm looking for the final height. There's one equation that relates all of those. That equation is I write it in a different order every time I write it down, it seems. That equation. Now, what's beautiful about this problem? We used the 3 common parts of the kinematic equation. There's only 4 of them. These are the 3 common ones, all in the same problem. Yeah, got to use them all. So I'm looking for y2, so I got to divide everything by 2a2. And then I have to add y1 to both sides. And I have y2 equals y1 plus that over 2a2 equals 88916 meters plus 0 squared minus 1991 meters per second squared over 2 times minus 9.80 per second squared. And that gives you 291. Well, there's more digits on this, but it's 291 kilometers, 291,000 some meters. So that was the calculation for the highest elevation it achieves. It was in the synthesis section because it required you to think through multiple parts of the problem. It wasn't just a linear, straightforward problem. And as I said the first lecture or two, that's why medical schools and dental schools require you to take physics. They want you to take these rather disorganized facts. I mean, it was succinctly written, but it doesn't tell you every detail. And then they want you to figure out how these are going to fit together in the medical setting to make a diagnosis, to understand what's actually going on with the patient. So that was the problem that had the lowest score. And then the next lowest score was a kangaroo can jump over an object 2.5 meters high. Calculates minimum vertical speed when it leaves the ground in order for it to clear the height. All you care about is clearing the height, so I only drew going up. And what I know for this is y final, again, specify y is the up direction. Y final is equal to 2.50 meters. Y initial is equal to 0. AY is equal to minus G, which is minus 9.80 meters per second squared. That's every value it gave me plus one that's inferred. What am I looking for? Actually, there's another. Looking for V initial. There is one more inferred value. What is the speed at the top?
0.
Okay, which kinematic equation is going to relate these variables? The one sans, one without time. So I'm just going to take the one without time. So I'm going to have 0 minus V initial squared is equal to 2 times minus 9.80 meters per second squared times 2.50 meters minus 0. Notice that both sides are going to be negative here. So multiplying minus across. So the starting speed squared is 49.0 meters squared per second squared, which means that the starting speed is equal to the square root of that. Seven meters per second. Okay, I've got a good 7 to 15 minutes to do some problems for you. I'm trying to spend more time solving problems in class. Now, you don't have clickers for this. This was set up as a clicker question. Just bringing it out. What forces are acting on a snow skier? Is weight acting on that person, the force of gravity?
Yeah.
Yes. What direction?
Down.
Down, because that's how we define down. Normal is normal force acting on the skier.
Yes.
Yes. In what direction?
Perpendicular to the
Not up. A lot of times we think up, but it's the direction that is normal to the surface, which when you say perpendicular, since it's a picture, it's a two-dimensional picture, you can use the word perpendicular. In a three-dimensional case, the word is normal. Same meaning. So in this picture, I can just draw the direction and we'll be all clear. Now remember, I put an F for all of my forces. So F sub n, force normal acting, normal to the surface, force of gravity acting down. Is tension acting on it, on the skier?
No.
No. Is a spring acting on the skier? No. Now, if you want to get all kinds of technical, sure, those skis are acting a lot like springs, but that's not what we're going to consider here. We're looking at the skier as a brick. So no. Friction.
Yes.
Yes, most definitely. What direction is the friction pointing?
Back up.
Force of friction. Air resistance.
Yes.
And that air resistance is really significant. One year, I decided to race Aaron Wong when I was sponsor of the Asian Student Association. And we go skiing, and I blew him away, all the way to the very bottom. When it went over this little roller under the lift. But when you're going really fast and you hit a roller, it makes you fly. I flew, I did not land it. I got up, had to walk back like 50 feet, got my ski and was putting it on when Aaron passed me. That's how far ahead I was. So the next year we're on the ski trip again. Aaron says, hey, you want to race again? Well, sure, guy's got to have his pride, right? What I didn't have was my courage. This time I get down on my tuck, I'd start whipping down the hill, and then I get scared. What if I have that crazy crash again, and I'd stand up? And when I stand up, what happens? Air resistance gets very large, and I slow way down. Then I get down on my tuck, I accelerate up. There's a thing we call terminal velocity. Terminal velocity is the velocity when you have the resistance force is equal to the force pushing you forward. In which case, what's your net force going to be? 0. And when the net force is 0, your acceleration is 0, which means that your velocity doesn't stop. Now, I had a really great time reading through the scrapbooks, and one person had a problem where they were testing or measuring the speed of raindrops and found that there's some raindrops that are traveling faster than terminal velocity, which is crazy. And their conclusion was that they were bigger raindrops with a higher terminal velocity that had broken into smaller raindrops, and now they have bigger air resistance, so they actually are having an upward net force. They're accelerating upward until they slow down to reach the terminal velocity. So it was really interesting. By the way, what do you suppose the most common item was on all the scrapbook pages? The Tesla. The Tesla automobile was by far the most popular item. It was on, 6 or 7 of the scrapbooks. Okay, buoyancy, lift, fluid pressure. Let's not talk about that. I'm going to briefly introduce some additional forces. The spring force, you might remember we had it in the slide last, Friday? But I said I'm not going to talk about it now. Springs are things that apply a force to bring them back to their original length. Springs also tend to get hung up in everything. So here's a spring. If I put a mass on it, the mass is going to apply a downward force, which stretches the spring, but the spring will make an upward force that gets bigger as it stretches. So now it's reached equilibrium. The mass is not accelerating up or down. We call it equilibrium when it's equal forces. That librium thing, the abbreviation for pounds is LBS, because it's libras, or force. So springs make a force that's proportional to how much it's stretched, or if you compress a spring, to how much it's compressed. And so the equation for that force is a constant that depends on the spring multiplied by the amount you stretched it or compressed it from its equilibrium length. So for this spring, its equilibrium length is the distance between those two ends right now. If I pull it out, it's going to have a force that pulls in proportional to how much I stretched it. That's how springs work. We call this equation here, by the way, Hooke's law. That minus sign is for direction. If you make it longer, the spring is going to pull it shorter. If you make it shorter, the spring is going to push it longer. That's what the minus sign tells you. Friction is a really interesting one. First of all, what causes friction? Friction is caused by two fundamental things. You have the conformation between surfaces. I like to illustrate this with my fingers. If I put my fingers like this, they kind of conform, they interleave a little bit. And so if I want to make them slide against each other, I actually have to raise up one of my hands to make it move. And so the roughness of the surface allows things to push sideways. That's part of what causes friction. So by making smooth surfaces, you'll reduce friction quite a bit because you don't have that conformation. You don't have things slipping down between others. Second thing is actual adhesion between atoms and molecules. Sounds ridiculous, but you do have forces that attract atoms between two surfaces. And so that's the second part of it. So you totally can't see the bottom because of this, so let me hide it. We have two kinds of friction we talk about. Static friction is friction when there's no motion between the surfaces. In that case, the static friction will be whatever force is necessary to keep them from sliding, up to a maximum limit. The maximum limit being the force that would be required to make it pop up just that little amount and start sliding. Because you have the pop-up part, the maximum limit for static friction is higher than what you're going to have for the force when it's sliding. So static friction is mu, that's the Greek letter M. In this case, it's the coefficient of static friction times the normal force. So if you have more normal force, if you have an object pressing into the surface harder, it's going to be harder to make it slide. It's proportional to how much you push in. Notice it's not proportional to area. If you have a bicycle tire or if you have a big fat tire, if it's rubber on asphalt, the same coefficient of friction, mu sub s, and the same normal force, the same weight on it, you actually have the same frictional force according to this equation. Now, in real life, there's more than what we have in general physics, but just keep that in mind. Surface area is not part of it. Kinetic friction, when they're sliding, the direction of the kinetic friction, as pointed out by Ryan, is going to be the direction opposing the motion. So if the skier is going down the slope, the kinetic friction is pushing up the slope. It's going to be whatever direction is opposing the motion. And the kinetic friction, I have a mistake on this slide that I didn't notice until right now. The kinetic friction has the equal sign. The static friction has the less than or equal sign. I have those opposite places. The kinetic friction has a different coefficient, notice mu sub k, that's smaller than the mu sub s, less friction, still proportional to force normal. Where is this useful? Automobiles these days. I finally have a car for the first time ever, well, actually I've had it for 6 years now, that has anti-lock brakes. Anti-lock brakes are designed to give you some real advantages driving if you're not a pro driver. A pro driver could do better without anti-lock brakes, but most of us aren't to that level. So what do the anti-lock brakes do? When you panic, what do you tend to do when you're driving? You brake hard. You just say, I'm going to push my foot through the floor on this brake pedal, and that's going to make me stop quick. Well, in fact, it doesn't make you stop as quick as if you braked optimally, because this is what your force looks like. Up to here is static, and out here is kinetic. If you have static friction, so you push down hard on the brake and the wheels slow down, the friction force increases until you reach a maximum limit. But when you reach that maximum, mu sub s times force normal, then you start sliding and it drops down. So this level here, mu sub s times force normal. This level here is mu sub k times force normal. So when you start sliding, you have less frictional force. So what do the anti-lock brakes do? As soon as your car detects that you started sliding, they will release the brakes and then hit the brakes again. And so your actual force is this kind of sawtooth thing. Every time it starts to slip, it releases and then brakes. And so the average force you're getting is higher than what you would get if you were just stomping on the brake pedal. Of course, it doesn't feel that great because you've got all those jerks every time the brakes lock, release, lock, release, lock, release. But they're giving you a higher force of friction, stopping you quicker. There's a second thing they do. If you lock up the brakes, you have no steering. You have steering equivalent to having a rudder, which isn't very much on the asphalt. So you really have no steering when you lock up the brakes. But with the anti-lock brakes, if your front tires are not locked up, you still maintain steering ability. So you can control the direction you're traveling when you panicked and slammed on the brakes. So there's two really good reasons for anti-lock brakes. Now, like I said, with a pro would brake until they get up to here and just keep it about there the entire time, and that would be the best overall. But you have to really know your car and your brake, your friction. Here's coefficients of friction between materials. Notice that the coefficient of friction between rubber and dry concrete is really high. You can get a braking force equal to the weight of your car if you have rubber on dry concrete. Doesn't have asphalt on there, does it? Kinetic friction 0.7. Notice your static friction is about on wet concrete is about the same as your kinetic friction on dry concrete. And then you can go down to other things. The other side of the coin, We use Teflon. Teflon on steel is a very low coefficient of friction, very low. So Teflon coated steel, very low friction. Things like in your car engine, you'd like that, right? You don't want to have friction between your crankshaft and your tie rod. You just want it to go around like this. And so they make a bearing that is, I believe, Teflon on steel. They lubricate it with oil to help to keep that from actually touching as much as they can. And you notice that God created us with a very low friction system for our joints, which is good. So just some references there. Talking about terminal velocity again. There are two different laws relating to the wind resistance we have. One law is called Stokes' law. That's the one on the right. Stokes' law is the equation that applies when you have a relatively low speed. With relatively low speeds, the air resistance force is proportional to the speed of the air. And then you have the drag equation, the one on the left. That's the one that is applicable at higher speeds. And in that case, the drag force, the force resisting motion, is proportional to the speed squared. So it's kind of complicated. I don't think I'm going to have you actually use these equations, but I can ask you conceptual questions about them. Right? So I can ask you, what's the difference between the drag force and the Stokes' law wind resistance? And the difference would be the Stokes' law has proportional to wind speed, whereas the drag force is proportional to wind speed squared. So this actually helps you to understand fuel economy in a car. Because if you're driving on a highway, because life is a highway, right? You're going at a constant speed of, let's say 80 miles an hour. Well, at 80 miles an hour, you're going to be having that drag force. The force against you is proportional to your speed squared. So you have wind slowing you down. Now, if we look at a car, let's draw a picture, a free body diagram for the car. There's our car. Car is traveling that direction. I was going to make it travel the other direction, but my picture looked like that would be the better choice. What forces would be acting on that car? Name them.
Engine.
I heard engine, but that's not one of them.
Weight and gravity.
Okay, I have the force of gravity. Force of friction. What direction is the force of friction? Now, when he says friction, I assume he means friction between the tire and the road.
Yes.
Which way?
Opposite your velocity.
Is it, okay, you said opposite velocity? Turns out that's wrong. That was actually the one that I wanted to make sure we got understanding on, especially for lab next week when you're going to be drawing this free body diagram. The force of friction is pushing the tire forward. Somebody said force of engine. The engine is making the drive shaft turn, which goes through the differential, which then makes the wheels turn. It puts what we call a torque to the rotational equivalent of force. And then the tires are pushing the road. The tires are pushing the road backward. And the road, according to Newton's third law, is applying an equal and opposite force to the tire, pushing forward. I was looking at only the forces of acting on the car. And so the tire pushing back on the ground is not acting on the car, it's acting on the ground. Free body diagram is only the forces on the object I'm interested in, the car. And so the force of friction is the forward one that's pushing the car forward. So when you're driving your car, it's the force of friction that makes it go. No force of friction, you can make those tires spin as much as you want. You don't go anywhere. Okay, so we got the force of friction. What other forces are there? Okay, there's the normal force. And there's the force of air resistance. If you're going to travel at a constant speed, what can you tell me about those forces? Constant speed means your acceleration is 0, hence net force is 0. Because Newton's second law, net force, mass times acceleration. So if you're going to travel at constant speed, the force of friction has to equal the force of air resistance, and that force of friction is countering the force you're putting to the tire. That's countering the energy you're putting into your engine. So the bigger the force friction necessary, or the bigger the air resistance, the more energy your car has to put out. Since that force of air resistance is proportional to speed squared, you speed up a little, the energy requirement is a lot higher. So how can we get better fuel economy? Ultimately, the goal would be if we can make this drag force smaller. Well, the drag force has to do with the density of the air. We don't have much control over that, although the density of the air is a fair amount lower up in Colorado than it is here, which means you should actually get better fuel economy just because you have a lower density of the air there. You have the cross-sectional area of your car. The cross-sectional area is, if you look at the silhouette from the front, that's it. If you can make that smaller, you can have less air resistance. So these cars that look like a Javelin, like mine here, they're going to have less air resistance, so they're going to have better fuel economy just based on their shape. Now, why they do it's not for fuel economy, so they can go faster, but it's the same outcome, less air resistance. And finally, there's that C. The C is a factor that has to do with the shape, and a lot of stuff goes into that. Tension, I've already talked about. Let's get to solving problems. So here's a problem. Tarzan has a mass of 84 kilograms. Find the tension of the vine if he hangs stationary. How do I approach a problem like this? First thing is to sketch Tarzan as shown. Second, use arrows to draw the forces. So Tarzan is my object of interest. I have to identify my object of interest before I draw the forces. So I'm going to draw the forces acting on Tarzan. So I have a downward force that's due to gravity. What's the equation for the force of gravity? Force of gravity is equal to mg. And it's from this that I like to use the units for forces. The units of mass, kilograms. Units of gravity, which is an acceleration, meters per second squared. So force has natural units of kilograms times meters per second squared, which we call newtons. So the force of gravity is mg acting down. The force tension is the force applied to Tarzan by the vine. And tension forces are always in the direction of the string going away from the object. So since Tarzan is hanging below the string, going away from Tarzan on the string is upward. So that's how I know the direction for the tension. So I have the forces drawn, not there. Here I have the forces drawn correctly. I started to circle the middle one, but it had an extra force drawn on it. Because that wasn't acting on Tarzan. That was force Tarzan was acting on the rope that was drawn. This here is taking just the forces that were acting on Tarzan and taking Tarzan away. You don't have to do that, but that's technically what a free body diagram is. So then I take that picture and I apply Newton's second law. So I say the sum of the forces is mass times acceleration. If he's hanging stationary, what's his acceleration? 0. Because if he's stationary, his velocity is constant. And if your velocity is constant, the acceleration is 0. He could be traveling constant speed, it would still be 0, but this is a case where it's 0. And so I look at my picture, using up as positive. I have tension minus the weight is equal to mass times 0. Therefore, tension is equal to the weight is equal to mg. That's how you solve Newton's second law problems. I have to show this because, believe it or not, Nathan and I had the same injury. We both have the sign of Zorro on our ring finger on our right hand. Both got it from playing flag football. You have tendons that pull your digits. And in both of our cases, our finger got stuck in somebody's clothing. and it snapped right there. And so no longer could we move this because we couldn't apply a force due to tension with that ligament. There is physics in our bodies everywhere. The picture down below, a very practical example for bicycle brakes. Bicycle brakes, you have a lever here, the brake. You pull on that lever, and it pulls a little cable that's through that protective nylon outer, goes to the end of that cable, applies a tension equal to the tension you made on the brakes. That force pulls the calipers to brake. I should point out something nobody put in their scrapbook was a picture I saw this week of a professional motorcycle racer who got released by his team because in the middle of a race, he reached over and pulled the brake on a competitor's motorcycle. That is so dangerous. Okay. My goal was to do this problem and then have you solve a variation of the problem. I'm not going to have you solve the variation of the problem here because there's only 3 minutes left. I have this guy on the rope. The guy has a weight of 840 newtons. Free body diagram's already shown. The tension of the strings goes in the direction of the strings. And the question is, how much tension is going to be necessary to hold this gentleman up? How would you approach a problem like this? Okay, with trig. This is actually most easily solved with trig. But you have to start with Newton's second law. The sum of the forces on that high wire dude equals 0 because he's not accelerating upward or downward. And so if I look at the forces, that would be tension left vector plus tension right vector plus weight vector equals 0. And now I'm going to use my ability to add vectors to draw a triangle. So tension left vector goes like this. Tension right vector goes like this. And the weight vector goes straight down. The tension, based on the symmetry here, I can immediately say the tension is going to have to be the same magnitude left and right because of the symmetry. And so I look at this and I can just say, well, now I have a triangle. I have two sides, tension left and tension right, the base weight. I can use my trig relations and the angle between, well, I know all the angles here, as luck would have it, to find what the tension is in terms of the guy's weight. So let's just do this the most obvious way possible. And that's not it. I have the angle, those two half angles were 5, so that means the full angle here is 10 degrees. And so I will use, should I use the law of sines or law of cosines? How about law of sines? Law of sines is easier. If that's 10 degrees, then this is 85 degrees, and this is 85 degrees because of the symmetry. And I can use the weight over sine of 10 degrees is equal to tension left over sine of 85 degrees equals tension right over sine of 85 degrees. So that means tension left equals tension right equals weight times sine of 85 degrees over sine of 10 degrees. Now, our time has run out. We don't have time to put that in the calculator, but using trigonometry made it easier than the way I normally would have done it. Next class period, I'll show you the way I normally would have done it. But since DJ chose the easy way, I figure I'll show you the easy way, especially with the time. Okay, have a good day. I'll see you Friday.